In the last lecture, we developed a general approach for analyzing wave propagation inside a waveguide. In this lecture, we take specifically a waveguide whose cross section is rectangular, and that waveguide is called a rectangular waveguide. So, we have a waveguiding structure for which we have a hollow pipe whose cross section is rectangular, and the energy is going to flow along the length of this metal pipe. We are again considering that this pipe is made of ideal conductor, that means the conductivity of this pipe is infinite, and the medium which is filling this waveguide is ideal dielectric, that means the conductivity of the medium which is filling this pipe is 0. So, we are having a very ideal structure, that is the pipe is ideal conductor and the medium filling this waveguide is ideal dielectric, and we want to now investigate how the electromagnetic energy is going to propagate inside this pipe. Without losing generality, let us orient our coordinate system so that the z axis is along the length of the pipe, that means that is the direction in which the energy is going to propagate. So, let us say this direction is the z direction, and then horizontal axis let us say is x axis. So, this axis is x and this vertical axis is y. The origin is located at one of the corners of this cross section. Now, considering in general this cross section of this waveguide is rectangular, let us say the width of this waveguide is denoted by A and the height of this waveguide is denoted by B, and by definition A is greater than or equal to B, and why we are taking that convention will become clear when we define the particular type of mode. So, here we are assuming that by definition A should be greater than or equal to B, and x axis is oriented along this broader dimension, that means along A. That is the convention essentially we are taking. Now, firstly, if we try to see whether TEM mode exists inside this, the answer is no, the TEM mode cannot exist inside this structure, and the reason for this we will see a little later after we have understood the TM and TE propagation. So, first we will take the simpler case, which is the transverse magnetic propagation. That means for this the Ez is not equal to 0 and Hz is equal to 0. We saw in the last lecture that if the transverse field have to exist, then either Ez or Hz have to be non-zero. So, in this case if I consider Hz is 0, that means the magnetic field now is in the oriented in the transverse plane, and longitudinal component Z component is only Ez. So, this mode we can call as the transverse magnetic mode. Or as we called earlier, in short this is called the TM mode. So, let us investigate now the problem for the transverse magnetic mode, for which the longitudinal component is only Ez and Hz is equal to 0. Of course, Ez and Hz both or all field components for that matter have to satisfy the wave equation inside this structure. So, the approach now is as follows. First we solve the wave equation for this longitudinal component Ez, then we go to the expression which we have derived last time for the transverse components, substitute here for Ez and Hz equal to 0, and we will get the transverse fields for the transverse magnetic mode. So, problem essentially has to be solved in two steps. One is first finding the solution for this longitudinal component Ez, then finding out transverse components, and then applying boundary condition, finding proper solution to this structure which is rectangular waveguide. So, if I take the wave equation in Cartesian coordinate system, this Ez is a scalar quantity. So, we can write down the wave equation which is del square E z plus omega square mu epsilon E z, that is equal to 0. This is the wave equation. So, this equation is a scalar equation essentially, and omega is the frequency, mu is the permeability of the medium, and epsilon is the permittivity of the medium which is filling this waveguide. We can expand this del square in the Cartesian coordinate system. So, we can get d2 Ez by dx square plus d2 Ez by dy square plus d2 Ez by dz square plus omega square mu epsilon Ez, that is equal to 0. Now, we solve this problem essentially just on mathematical considerations. However, since we have developed the understanding for the wave propagation inside the parallel plane waveguide, we make frequent visits to that understanding. So, whenever we choose some constants or something while writing the solution to the equation, we make sure that whatever solution you get, that solution should be consistent with what understanding we have developed from the parallel plane waveguide. Now, this equation can be solved by separation of variables. So, we can define this quantity Ez, which is product of the 3 functions, each one is a variable of either x, y or z, and of course, there is the implicit assumption that all these fields are varying as a function of time, which is e to the power j omega t. So, we can say that we can apply separation of variable to get a solution which is a function of x, y, z, that is some function of x, some function of y, some function of z. Now, if you recall, the wave is propagating in the z direction, that means we are looking for a solution of travelling wave type in the z direction. And since we are considering a medium which is completely lossless, because the dielectric is ideal dielectric, the conducting boundary of this waveguide is again ideal. So, there is no loss anywhere. So, we have a sustained propagation of wave inside the structure. So, we have z variation for a travelling wave in the z direction, which will be e to the power minus j beta z. That information we will use when we try to solve this problem, that we are looking for a travelling wave solution in this direction. Also, we have a information from parallel plane waveguide, and that is, let us say, suppose I make one of the dimensions of the waveguide, I push it up, let us say I make b equal to infinity, then essentially I got a structure which is a parallel plane waveguide. And I have seen for parallel plane waveguide that this can be visualized as the propagation of uniform plane wave inside these parallel planes by multiple reflection on these 2 planes. So, it creates standing wave kind of patterns in this direction, which is perpendicular to the planes, and a travelling wave propagation along the planes. So, that means whatever solution we are going to get for this problem must have a standing wave kind of solution in the x direction, because if I take a limit when b tends to infinity, the solution must represent the solution for the parallel plane waveguide. Same is true for this also, that if I take these 2 planes, then if I take a tending to infinity, again I will get a parallel plane waveguide which is horizontal now, and then I must get a standing wave kind of solution which are in y direction. So, the physical understanding tells me that the solution which you are getting along the x direction must be of standing wave type. The solution which we should get along the y direction also must be of standing wave type, and the solution which we should get along the z direction must be of travelling wave type, because in that direction the wave is going to, net wave propagation is going to take place. With this understanding, now we are going to solve the problem. So, first let us just take this and blindly substitute into this equation. So, if I substitute into this, I get y z d2x by dx square plus x z d2y by dy square plus x y d2z by dz square plus omega square mu epsilon x y z, that is equal to 0. Note here, now the partial derivatives have been converted to the full derivatives, and the reason is x is now a function of x only, y is a function of y, and z is a function of z. By dividing by x, y, z all these terms, essentially we get 1 upon x d2x upon dx square plus 1 upon y d2y upon dy square plus 1 upon z d2z upon dz square plus omega square mu epsilon, that should be equal to 0. Now, this quantity is only a function of x, this quantity is only a function of y, and this quantity is only a function of z, and this is constant. Now, this equation whatever you have written, it should be valid at every point in space. So, this equation must be satisfied by every point x, y, z in the 3-dimensional space, and that can only happen provided each of this term is a constant quantity. So, this should be a constant, this should be a constant, this should be a constant, then and then only this equation can be satisfied by every value of x, y, z. So, what we do is we just take each of these terms and equate them to some constant, and the equation essentially reduces to 3 equations, and that is 1 upon x d2x upon dx square is equal to some constant, and let me just put the constant as minus a square. Second term, which is 1 upon y d2y upon dy square, let us put that thing as minus b square, and third quantity, which is 1 upon z d2z upon dz square, that is equal to minus beta square, where beta is the phase constant of the mode of propagation. We have chosen here this negative sign appropriately, so that the solution which you get for this equation, that will be a standing wave kind of solution in x direction, a standing wave kind of solution in y direction, and a travelling wave kind of solution, as we will see, will be given by this phase constant beta. So, while writing the expression for x, y, and z, essentially we make sure that we write a solution which will look like standing wave kind of solution and travelling wave kind of solution as a function of x, y, and z. So, this equation to solve is very straightforward. So, this is, I can multiply x on this side and take the term, this will be d2x upon dx square plus a square x equal to 0. So, it is a second order homogeneous equation for which the solution can be written in a straightforward manner. So, we get the solutions. So, the capital X as a function of x will be some arbitrary constant C1 cos of Ax plus some other constant C2 sin of Ax. Y as a function of y will be some constant C3 cos of By plus C4 sin of By, and z as a function of z will be C5 e to the power minus j beta z plus C6 e to the power plus j beta z. So, note while writing these solutions, these functions which are the cos and sine functions, they show amplitude variation, which is the standing wave kind of behavior. Whereas, if I look at this quantity e to the power minus j beta z, that represents a travelling wave in positive z direction. If I consider e to the power j beta z quantity, that represents a travelling wave which is in negative z direction. So, while writing these solutions, first we use our understanding which you have developed with the parallel plane waveguide, that is, in the transverse direction between the two conducting boundaries, we must have a solution which is like a standing wave kind of solution, and along the length of the pipe in which the energy is going to propagate, we have a travelling wave kind of solution. Now, in general, when we have this wave equation solution, of course, there are two waves which are travelling on the structure, one is in positive z direction, one in negative z direction. However, if I assume that this waveguide is of infinite extent in z direction, then there is no reflected wave on this, because we have seen from transmission line that if I take an infinitely long transmission line, there is no reflected wave on this. So, we can, just for simplicity of the analysis, we can assume that there is no wave which is travelling in the negative z direction, and we have only one wave which is the forward wave which is on this waveguide. So, this wave as shows is a forward wave travelling in positive z direction. So, let us assume that only one wave which is travelling in positive z direction exists, and there is no wave which is travelling backwards on the structure. So, we can assume that for no backward wave, we can take the C6 as identically 0. So, the Z solution is only C5 e to the power minus j beta z, and with that understanding, then I can write down the complete solution for the Ez, which is product of this and this quantity. So, from here then I can get Ez, which is the function of x y z, will be equal to C1 cos Ax plus C2 sin Ax, C3 cos By plus C4 sin By e to the power minus j beta z, and we are going to put a constant here which is C5. So, this is now the solution, general solution for the wave equation for this component Ez. Now, we can apply boundary conditions to get these arbitrary constants, and in this case we are having the Ez which is like that in the waveguide. So, this component Ez is tangential to this wall, it is tangential to this wall, it is tangential to this wall, and it is tangential to the lower wall. So, this component Ez component is a tangential component to all the four walls of this, and that is why we have four boundary conditions, one on this wall which is x equal to 0, one on this wall which is x equal to a, one on this wall which is y equal to 0, and one on this wall which is y equal to b. So, we have got four boundary conditions that all these four walls where x equal to 0, x equal to a, y equal to 0, y equal to b, this component which is tangential should be 0. So, we have a boundary condition now to apply on Ez, and that is Ez is equal to 0 at x equal to 0, x equal to a, and y equal to 0, y equal to b. So, I just use one by one boundary condition. If I put x equal to 0 in this quantity will be 0, sin of Ax this will be 0. Now, Ez is 0, that can happen provided this C1 quantity that should be equal to 0. So, I get from here, from the first condition, that for x equal to 0, this condition, we get this arbitrary constant C1 should be identically equal to 0. So, this gives me C1 should be identically equal to 0. Same thing we can do for from here, that since for y equal to 0 again Ez is 0. So, if I put y equal to 0, this quantity will be 0, and then if Ez has to be 0, this arbitrary constant C3 should be 0. So, we get for y to be equal to 0, you get the arbitrary constant C3 should be identical is equal to 0. Once you get that, then the solution essentially now has become C2, C4, C5 sin of Ax, sin of By e to the power minus j beta z. So, the general solution which can satisfy this boundary condition x equal to 0, y equal to 0 now will be Ez C5, C2, C4 sin of Ax, sin of By e to the power minus j beta z. Now, these are the arbitrary constants. So, we just combine this into one. So, this is just telling me the amplitude. So, I can say this combine all this thing combined together. Let me calculate this quantity as some c into sin of Ax, sin of By e to the power minus j beta z. Now, apply a second boundary condition that when x is equal to a, again this quantity Ez is 0, and that can happen when provided this a times small a, that quantity is multiples of pi. Similarly, from this boundary condition that Ez should be 0 for y equal to b, if this By is multiples of pi, then again this quantity will be 0. So, from these two boundary condition x equal to a and y equal to b, we get that a times a that should be equal to some multiples of pi. That means, this constant a which we still have to determine, that is equal to m pi by a. Similarly, or b times small b, that should be equal to some another integer of pi, and that gives b is equal to n pi by b. We can now substitute, once you get these constants a and b which are related to these dimensions, the broader dimension of the waveguide and the smaller dimension of the waveguide, and m and n are integers, this longitudinal component field Ez is constant c sin of m pi x by a sin of n pi y by b e to the power minus j beta z. This is now the complete solution of the wave equation for this longitudinal component Ez. We applied all the boundary conditions. This arbitrary constant c will remain undefined, because this essentially represents the amplitude of the electric field, and that has nothing to do with the boundary conditions, because boundary conditions are satisfied irrespective of the power level or the amplitude of the field. So, this parameter, this constant, arbitrary constant c, will remain as it is at this stage. When we really talk about the power inside a mode, then and only this quantity c will be evaluated. So, now we have got a complete solution, and these two quantities now m and n, which are integers, they now represent essentially the order of the mode by the same token as we have done for the parallel plane waveguide, that there we had a transverse magnetic mode and we had put an index. Now we can put the indices, which are these two indices for m and n. So, a transverse magnetic mode now can be designated by Tm with these two indices m and n. Now, here the convention essentially comes handy. Why we have taken a convention? The first index which we have here is the index around the broader dimension A. So, that is the reason we taken the convention that broader dimension is called A. That is the direction in which the x is oriented. So, the first index essentially tells me the field variation along the broader dimension of the waveguide, which is x direction. Similarly, this index n tells me the field variation along the shorter dimension of the waveguide, which is the y direction. So, when we write a mode Tm m n, the first index tells me the field variation along the broader dimension, the second index tells me the field variation along the shorter dimension. Also, we will note here that if m equal to 1, then when x varies from 0 to a, here you have essentially one half cycle variation. If I take m equal to 2, I have one full cycle variation, and then so on, and same thing is going to happen in y direction. So, this behavior is exactly identical to what we have seen for the parallel plane waveguide, that the order or the index which we have for the mode, it represents number of half cycles in the transverse direction, and in this case there are two transverse directions, one is x and one is y. So, along each of this transverse direction x and y, these indices tell me the number of half cycle variations for the magnitude of the field. So, if I take m equal to 1, then I get one half cycle variation. If I take m equal to 2, I will get two half cycle variations, and so on. So, once we have understood the field behavior for the parallel plane waveguide, visualizing these now for rectangular waveguide is very straightforward, because we have already developed the physical understanding of how the field variation is going to be. And as we can see, in the limit when a or b tends to infinity, this essentially waveguide will become a parallel plane waveguide, and then the expression which we had for Ez, or for that matter we will see later for Sz, that is identical to what is the expression for the electric field in the parallel plane waveguide. So, this field expression which we have got now can be reduced to the parallel plane waveguide by properly substituting either a equal to infinity or b equal to infinity. Now, once we have got these constants now m and n, there are a few things which can be noted from here. Firstly, m equal to 0, n equal to 0, if I substitute into these equations, the Ez will be identically 0. What that means is that Tm00 mode cannot get excited inside a rectangular waveguide. We have seen for a parallel plane waveguide that the Tm0 mode, which was same as the transverse electromagnetic mode, was possible in a parallel plane waveguide, and that was the mode which was the lowest order mode. However, for this mode, we note that when both the indices are 0, the field goes to 0. So, Tm00 does not exist. Also, we will note when any of the indices go to 0, then also again this field goes to 0. Sz is already 0 for transverse magnetic. If Ez also goes to 0, then all the field will identically go to 0, because H is not equal to 0. That is what we have to show. So, first let us show that for this mode H is not equal to 0. If I go back to the wave equation and substitute now this quantity from this equation, this quantity as we have defined as minus a square this quantity we defined as minus b square here. So, this quantity is minus a square, this quantity is minus b square, and this quantity is minus beta square, and we have found out now this value of a, which is m pi by a, this quantity is n pi by b. So, we can go back and substitute into this to get a relation which is minus m pi by a whole square minus n pi by b whole square minus beta square plus omega square mu epsilon is equal to 0. I can take this beta on one side. So, the phase constant for this mode will be equal to square root of omega square mu epsilon minus m pi by a whole square minus n pi by b whole square. Now, this relation is familiar. The similar relation we had seen for the parallel plane waveguide with only one term, which was omega square mu epsilon minus m pi by d, where d was the height of the waveguide, and this expression essentially tells how the velocity or the phase constant varies as a function of frequency on the structure. So, this expression is identical to what we have derived for parallel plane waveguide, and that is why this is the dispersion relation for the transverse magnetic mode on a rectangular waveguide. So, we can call this as the dispersion relation, as we saw in the last lecture. So, this is the dispersion relation for TM-MN mode, where m and n are these two indices which are non-zero. Now, if I take m and n both equal to 0, we saw the fields are not existing, but if I take m and n, one of them is 0, then this quantity now, this is h. What is h square now? The h square was defined as omega square minus beta square in our general analysis. So, we had defined this quantity h square was omega square mu epsilon minus beta square. So, by that, comparing this with this, we get essentially for this case h square is your m pi by a whole square plus n pi by b whole square. So, when m and n both are not 0, the h square is not 0. So, when the h square is not 0, the field which we have transverse fields which are represented in terms of the longitudinal components, we have seen the transverse component would exist if both of Ez and Sz are 0, provided h is also equal to 0. However, now we are seeing that h is not equal to 0 when either m or n are not equal to 0, and then if Hz and Ez both go to 0, all transverse field would go to 0 and the mode would not exist. So, we see that for the transverse magnetic case, when either m or n are 0, any of these two is 0, then again this field will be 0, and since h is not 0, again the transverse field will go to 0 and the modes will not exist. So, now we have some important conclusion drawn from this analysis for transverse magnetic mode. So, we have a mode TM MN mode. So, the first conclusion which we have is TM 00 does not exist. So, we also conclude that TM M0 and TM 0N also do not exist. So, the lowest mode which can exist, the lowest index, that is when both these indices are non-zero, that means TM 1 1 is the lowest order of TM mode which can exist on the waveguide. So, by doing this general analysis, we come to the very important conclusions that if the TM mode has to be excited on a rectangular waveguide, the fields must vary in both the directions x and y on the rectangular waveguide, and that we can see physically as follows. Since the index m and n is telling the variation, 1/2 cycle variation along the x and y direction respectively, when m is 0, there is no variation of the field along x direction. When n is 0, there is no variation of the field along y direction, but the field has to be 0 here. This is Ez component, so it has to be 0 here, it has to be 0 here, and there should not be any variation in the x direction if m is equal to 0. That is only possible provided the field is identically 0 everywhere. The same is true for these two boundaries, that when n is equal to 0, the field should not have any variation in the y direction, but it should be 0 here, it should be 0 here, and that again can happen when the field is identically 0 everywhere. So, physically it makes sense that yes, this field Ez cannot exist inside this without a variation in x and y direction, it must vary. Also, we have seen from the solution in this Cartesian coordinate that the variation is always sinusoidal and it is always number of half cycles. So, you can have 1 half cycle or 2 half cycles or 3 half cycles and so on. So, essentially we get now the variation in this, the Ez is always 0 on these two, and depending upon the value of m and n, you will have the variation in x and y direction, which is sinusoidal variation. So, the field in the transverse direction always varies sinusoidally in the Cartesian coordinate system, and they must vary, because if they do not vary in any of the directions, then the field cannot exist inside the structure for the transverse magnetic case. Of course, your conclusion might be different when we go to the transverse electric case, but these are the conclusion which we can draw now for a transverse magnetic case. Once we get now this Ez, then we can substitute for Ez into these components, and then we can write down the transverse components for the TM mode. So, we can substitute now Ez, the general solution which we got, and now if I write for Ex, Sz is 0, so this term is 0, this term is 0. So, I get now Ex, which is equal to minus j beta upon h square, where h square is already have been calculated. This is dEz by dx. So, that will be equal to minus j beta upon a square m pi by a into that arbitrary constant c cos m pi x by a sin n pi y by b and multiplied by e to the power minus j beta z. Same thing I can do for E y, that is equal to minus j beta upon a square dEz by dy, which will be equal to minus j beta upon a square n pi by b c sin of m pi x by a cos n pi y by b, and this face term e to the power minus j beta z. The magnetic field on the same lines we can get as j omega epsilon upon s square dEz by dy, that is equal to j omega epsilon upon s square n pi by b c sine of m pi x by a cos of n pi y by b e to the power minus j beta z, and h y will be equal to minus j omega epsilon upon s square dEz by dx, that is minus j omega epsilon upon s square m pi by a c, like this, cosine of m pi x by a sine of n pi y by b e to the power minus j beta z. So, now we got the complete fields for the transverse magnetic modes, with the understanding that the lowest order mode which is going to propagate on the structure will be the TM11 mode. Now, a few things can be seen from here, and that is the Ez component, which is the for which we obtained a solution, that essentially is 0 at these 4 walls. So, it is having a sinusoidal variation. So, we had a Ez variation which is this. So, the Ez was 0 x direction at x equal to 0. So, both the walls the Ez was 0, Ez in y direction also having half cycle variations. If I look at the cross section like that, or the waveguide, the Ez is 0 here, 0 here, 0 here. So, it had half cycle variation like that, or it could have a variation which will be like that. The same is true for half cycle variation in this direction, or it could be like that. So, the Ez is 0 at this point, and the maximum here if m is equal to 1, maximum here along this if n is equal to 1, and so on. However, if I look at this field now, which I got here Ex, Ey, Hx, Hy, the Ex is having a variation which is cosine variation as a function of x. So, the component Ex, which is this x component which is oriented this way, it is having a variation, cosine variation along x direction. That means it is maximum here, 0 here, and another maximum here. Again it is half cycle, but it is not 0 here, or in other words it is shifted like a quarter cycle in space with respect to the Ez component. So, the Ex component, if I look at this, will be, it will be like that. This will be the component which is Ex. So, that is maximum here, 0 here, maximum here. But the Hy component, if I look at, it will be again a cos variation along y direction. So, it will be in this direction. If I look at, the field variation would be like that for the Ey component. So, now later on we will try to visualize these fields actually inside this pipe, but at this point it appears that the component Ex, Ey, Hx, Hy, depending upon the boundary conditions, they will be staggered in space in the transverse plane with respect to the longitudinal component which is the Ez component. Once we get this understanding that the electric field which is like that is maximum on this boundary, And if I look at the magnetic field, which is, let us say I take x oriented magnetic field, which is having a variation, which is sign variation in the x direction and cos variation in y direction. So, if I consider now a magnetic field which is x oriented, then it is cos variation in y direction, that means it is maximum here, 0 here, maximum here, because Ex and Hy they have the same behavior and Ey and Hx have the same behavior. If I compare these expressions, this is what essentially we see. So, what we observe from here, and of course from rigorous analysis also we can do that, but what we observe from here is that Hy component, which is this, is maximum on this wall and on this wall. That means when the magnetic field is tangential to the boundary, that is where it is maximum, and of course it is having a variation which is sinusoidal variation with number of half cycle depending upon the order of the mode. Similarly, here when I consider Hx, it is going to be maximum here, maximum here. That means magnetic field is maximum when it becomes tangential to the conducting boundary, and the electric field is 0 when it becomes tangential to the conducting boundary. Of course, the tangential magnetic field, whatever is there on the boundary, is balanced by the surface currents. So, there is no boundary condition on the tangential component of magnetic field. So, essentially by using this observation that the magnetic field is maximum, tangential component of magnetic field is maximum on the conducting boundary, and having understood that the solution gives me a sinusoidal variation in the transverse direction, now we can readily write the solution for the transverse electric mode without going to the same analysis. Of course, in a routine way we can do the same thing, that if you want to analyze the transverse electric case, then we take Ez is equal to 0, we take Sz not equal to 0. So, we consider a case which is transverse electric case or a TE wave. So, in this case the longitudinal component which we have is Hz, which is like that, and now what we observe from this is that this component, which is going to be tangential to this wall, this wall, this wall and this wall, should be maximum on the walls, and it should have a variation which is sinusoidal variation in the transverse direction. So, now having understood all this analysis, we can write the solution without going to the same steps, same algebraic step which we have done. We can get the solution for Sz, which will be some constant cosine of m pi x by a cosine of n pi y by b e to the power minus j beta z. So, without repeating the algebra which we have gone through for solving the wave equation, of course I can go the exactly same way. I can solve the wave equation now for Hz, then apply the boundary conditions, but note directly on Hz there was no boundary condition. So, if I have to go from the same routine way, then I have to find out general solution for Hz, find out the transverse component, then find out the component which are tangential to the boundaries, and then apply the boundary conditions on those components, because tangential component of magnetic field there is no boundary condition. So, in this case TE case, if I go by the routine way, there will be two steps involved. First, find out the general solution for Hz, substitute into the transverse component expressions, find transverse components, and then apply the boundary conditions on the transverse components, because intrinsically there is no boundary condition on Hz. However, without going to the same routine steps, essentially the understanding which we develop that the magnetic field when it becomes tangential to the conductor is maximum, I can get the expression for Hz, and one can go and verify that if I had done the rigorous analysis, essentially I would get the same expression. Now, this you can verify when x is equal to 0, the field is maximum, the x is equal to a, again the field is maximum, y is equal to 0 and again y equal to b, again the fields are maximum. So, these fields are having the variation which essentially we are looking for, the tangential component of magnetic field must become maximum. Using this expression for Hz, now we will investigate the transverse electric mode and see the characteristics of transverse electric mode and then compare the behavior of this mode with the transverse magnetic case. So, we will continue the discussion on the transverse electric and transverse magnetic mode inside a rectangular waveguide and see more properties for these modes.